Okay, we are recording. I'll go back to the slides, and I think this is where we were last time, right? Like we were looking at pooling operation. I hope everyone was clear with the ideas of pooling. If there are any questions, please let me know. We can quickly discuss them. If not, we can move on, right? So we looked at mean pooling and max pooling. So we are probably at the part of the architecture where we have, um, you know,
Sir,
the.
can you share your screen, please?
Did I not do that?
No.
I'm very sorry. Okay, I forgot. Thanks for reminding. Okay, there you go. How about now? Yes.
Yeah, thank you, sir.
There. All right. Perfect. Okay, so we were here, right? So we are looking at pooling approaches, mean pooling, max pooling. We are looking at what sort of resultant output they can give us and what it means, how to interpret that, and uh, we were we're probably at the part of the architecture where we have now extracted features, reduced the feature dimensionality, and now we are ready to do something with it, right? That's the place we are at. So just to summarize this part very quickly, now the reduction in the dimensionality is very important because often it seems like if you have too many parameters, then it becomes harder to train the network. So the fewer parameters helps, so it's easier to train the CNN. So that's number one. That's very this and leads to selection of features over a broad spatial scale. So the idea is, if you go back to the receptive field concept, right? And when we were talking about that, when you look at the very earlier layers, they look at very small part of the image. But then as you go further and further, right, then now you're looking at a little bit bigger part of the image, and then, and so on and so forth. So the spatial scales are changing across the layers, right? As you're going across each of the convolutional layers, the amount of information that a single neuron at a given level sees is a bigger part of the input space than what was happening at a much shallower layer. So in sense, it's getting a much broader picture, and that broader picture can help it understand the whole image rather than tiny parts of the image, which was what we were discussing in the initial examples of the Samoyed versus wolf, and then the Samoyed in two different lightings and so on, right? At the lowest levels, even though they are different, at the most abstract levels, they are the same thing. So in order to make that judgment, we need to look at the entire image as a whole rather than its individual parts, and this helps you do that. Okay, but once you reach to this place, right, once you get this nice low dimensional representation which preserves some form of spatial correlation, right? So it preserves some amount of spatial relationships in the image because that's how the network is designed. What do we do with it, right? Now, if you can imagine, as I was mentioning, this can be thought of as some form of an embedding of your image, right? And you can use this for many things, right? This can be used as a way to say um, decompress, or sorry, compress the image, which can be then decompressed out using a deconvolutional network. You can use this for classification and prediction. The most commonly used idea is to place a dense layer on top of this, or what's called a fully connected layer, right? And we know that these dense layers or fully connected layers are really good at performing classification of prediction problems, right? We looked at that when we started off. So, in essence, this final low dimensional representation can then be used to classify between different types of images, right? Like this information can be then passed through any sort of network that has a specific form of role, right? So let's look at that. So what was my final point here? Yeah, the deeper we go, the abstract the features we want it to be. So the pooling helps that, right? Like we want abstract features, we want something that tells about the image as a whole rather than its very small individual parts. So that's what the pooling operation helps you do, right? Now, moving on and talking about the fully connected layer and the idea of softmax, this is what we saw, right? So we are here now, right, at the end. So we got a nice low dimensional representation, and now we can project that onto a dense layer, right? Now the dense layer can be again many layers in length and in size, all right? And this is again a full feed forward network, which at the end of the day is trying to predict some aspect of the input. In this case, it's doing image classification. We're trying to find out whether it's a horse, zebra, or dog, right? Something like that. So this part kind of does the classification. That is, you are able to separate out this space and project it into probably a higher dimensional space in this case, right? Which is able to separate out horse, zebra, and dog effectively, right? And there is a probabilistic aspect to it where the activations of the output layer here are converted into probabilities in order to make a judgment about what likely is the model's output towards a specific input image, right? So for that image, what is likely the class of the output? Okay. So this is what it is. This we kind of understood what this actually does, right? It transforms your input space or morphs the input space into a space that can make it more linearly separable. And since this preserves the spatial relationships among the image, there is a better chance that if you provide such an embedding to this network, you will get a better classification. So then that's what convolutional neural networks are really, really good at doing. Okay. Now, what is this part, right? Like this part we understand. What is this probabilistic distribution part? So idea of the softmax operation, which is typically used to convert the final level activations into probability distributions. That is, in this case, you have three values, Z1, Z2, and Z3. They can range between, depending upon the type of activations that you use in your fully connected layer, if it's a tan H, if it's a sigmoid, or so on and so forth, right? Then the values can range between, say, -1 to +1 or 0 to 1, depending upon that. So let's say we have a tan H activation function, and it varies, right? So let's say Z has some value, Z1 for a given image has some value of 0.9, and this has 0, this has -0.2 or something like that. Let's say, okay, that's the classification. It's 0.9 horse, so let's say it's 0.3 zebra and -0.2 dog. Okay. Now, the problem is, how do you pick from out of these one that is, talking about which is the likely output given the image, right? Like we want to understand that what is the model's prediction given a certain activation. Now, in this case, you can think of winner takes all, right? Like you can say, okay, the one that is maximally active is the one that's, you know, the one that is the winner, and that's what I'm going to select that. But there are issues when things become quite close to each other, right? Like let's say with the activation here is say 0.6, and in this case, say 0.5 and 0.2, for example, right? Now, how do you pick in this case, right? It could have been a zebra and a horse, but you need something much more concrete. So the idea came from here that let's normalize these activations using and then convert that into a probability distribution using a normalized exponential function. Okay, right? So this is the softmax operation where you are taking your activations, right, and then normalizing it by placing the activations on an exponential function and then dividing it by the sum of the exponentials. Anybody can tell me what is the intuition behind using an exponential function? Why do you want to use an exponential function to do this?
So we can see in the broader way, like normalization means we are shifting the scale.
Right.
We are not
So
wanting to
if I draw an exponential function, let's do that, right? Let's say this is x, this is z, sorry. This is sigma of z, right? Now an exponential function will look like this, right? Here it's 0, 1 or something. Okay, right? Because e power 0 is 1. So why not use, say, something like this, right? I can use probably a straight line too, like that. Why not use such a function, but why use an exponential function?
Maybe it's always positive. Probabilities can be positive.
In this case also it'll be positive, right? I'm having the line above the.
So, sir, like if the values are close, let's say the example that you gave, right?
Very good.
So the scaling will be, I mean, we can
Exactly.
differentiate easily.
Exactly. Very nice. Very nice. The scaling will be very different for an exponential function, right? So for instance, those values that are really different from each other will be amplified. So the difference between Z1 and Z2 will be amplified. And another advantage is obviously when you do this form of a normalization, what you end up with is with a probability distribution. That means when you take the sum of the values of Z1, Z2, Z3, they equal 1. So they make a probability distribution, which is very nice because now we can sample under the probability distribution, and then based upon that we can find out what is the output of the network or what the network is trying to predict, right? But as one of you rightly said, it's because of this amplification and the scaling, right? Like if there is a small difference between them, that can also be amplified because given the exponential functions, small changes in z will have large changes in sigma z, right? So that changes will exemplify. And the example that I gave you, when this is 0.6 and this
This
is
means a clear separation, right?
there'll be a clear separation between them, right? So, and that will amplify the differences and help us understand if the network is actually doing the job well, right? It could be such that the network is doing it really well, right? We are not able to amplify those differences and find it out. And this allows us to kind of do that, right? And that's why the reason why this is used, right? So the small differences can also get amplified and you can measure the network's performance in a much reliable fashion. So let's take an example. As I told you, one possible distribution could be something like this, right? Now Z1, Z2, Z3, Z1, Z2, Z3 have some activations, and this is a probability distribution. All of this will add up to 1. Okay. And how will you now pick how will you now know what value the network or what how would I say, what output the network is trying to predict here? By looking at the probabilities, you can find out Z1 is higher, but how do you actually find out what is being predicted at that given time? Any idea?
Sir, argmax.
Yeah, you can do an argmax simple and find it out. That will tell us this is what is being, which one basically. We don't need to even do argmax. It's basically a max, right? Max of z, sigma zi. It's fine. And then we find out, yeah, argmax, which z maximizes sigma of z. Then that'll give you this basically. But you can also sample under this probability distribution, right? And you will see that most number of times Z1 will be the one that will occur. And that also tells you that that's what the model is predicting, right? And there could also be a scenario where the model does not know among these things, right? Like when Z1, Z2, Z3 are almost similar, then they'll have equal probabilities. And in this case, you know that the model is uncertain about the output. Or in other words, we kind of understand maybe the model has not trained well enough in order to do this task effectively, right? So thereby your loss will depend upon how the sigma z is, because in these cases we use like a cross entropy loss, right? We looked at it before. And that way we are able to understand what the network is trying to predict, whether it is siding towards one of them or it's not able to distinguish, right? And typically in papers you will see percentage top 1 as one form of performance, right? So how much percentage of times that particular input was selected as the top input predicted by the model, right? And you compare that with your expected output or your actual ground truth, and then you can understand the nature or the performance of the model, right? And sometimes it's percentage top 5 is also used, right? So if you have 5 options, right, like if in this case horse, zebra, dog, cat, and everything, and then you can see if there is a probability distribution associated with it, whether that particular input occurred in the top 5, for example, right? So if it might not have been the first option, it could have occurred in the second. So if you presented the image of a horse here, and then maybe horse is the second best prediction by the model, right? So it's not then you can't use a percentage top 1 criterion, you can use a percentage top 5 then. So that's also a way to evaluate the model performance. And the softmax allows you to convert these activations into probability distribution, which then provides a way to do all these subsequent evaluation measures. Okay. Any questions here?
Sorry, sir, I missed what softmax will provide us.
Sorry, softmax will provide us the probability distribution, right? So it will give us the probability distribution over these activations.
Means by looking this, we are able to understand whose probability is
higher. Yeah, which options or which classes probability is higher, and thereby we can use this measure to evaluate the performance of the model, right? Whether our chosen input image occurs either in the percentage top 1, which is the topmost choice, or in the top 5. That is also another metric, right? It depends upon the number of classes you have. If you have a huge number of classes, then percentage top 5 is also a good metric to analyze. But if you have just 3 classes, then I would consider more percentage top 1 to be a better metric, right? It makes sense.
And sir, it doesn't always amplify, right? For instance, if you take negative values for Z, there it is almost stable. E power C. So then there it doesn't amplify, right?
There it does not. That's what. So okay, very good point there. The amplification happens in the positive side of Z, right? So that means whenever Z crosses a specific value, and it probably is on the positive half of things, right? That becomes and the negative half, since it is much more flatter, there you see that there is not much amplification, right? So in essence, if every value is negative here, right, then probability distribution will remain flat for all the 3 options. So yes, the amplification happens when one of them crosses this positive, jumps into Z being positive, and then if Z value increases, and the point is that it helps you separate things apart when you are closer in the it could be this or this, right? The model is unsure there, right? Then that becomes a scenario where the softmax works well. But if it does not know or doesn't have high activations for either one, the model itself is telling you that it's probably not any of these 3, right?
But in these cross entropy loss, anyway, it takes only the Z value, which
Correct.
has the maximum.
Correct. So, but not the Z values. The cross entropy loss takes the probabilities.
Yes, probability. But with E power Z or with something else also, the corresponding Z will have the maximum probability value, whether it can be 0.6 if you do this transformation, or some 0.4 with respect to other transformation.
Come again. So what do you mean? You mean to say that if I use 0.6 here and use a softmax transformation, that does not matter if I use some other Z value but use another transformation. Is that what you're trying to say?
No, same Z value.
Yeah.
But, so you plotted two transformations, right?
Yeah,
One is
yeah.
e power Z, one is that blue line.
Yes.
So irrespective of whatever transformation, given that the sum of probabilities is 1 by either of those, whichever Z value has the highest probability,
Yes.
using e power Z will have the same. I think we'll have the highest probability using some other transformation also.
No, I don't understand your question. So the point I'm trying to make here, I mean, okay, at least let me know if I understand your question right. So if you say that if you use another transformation, which will also give you probability distributions, there also you will use the highest value of Z in order to make a decision. Is that what you're trying to say?
Yeah. So among these Z1, Z2, Z3, let's say Z2 has the highest probability using e power Z.
Yeah.
I'm saying even if you use some other transformation, the corresponding value of Z2 only will have the highest.
I see. I mean, it depends. I mean, we should use such a sort of transformation that can scale such that the highest values of Z are amplified, right? And e power Z is one of them that can do that. There is there are, I think, other ones as well. I don't recollect. It's not coming on top of my head, but
okay.
But I mean, obviously there is a possibilities you can use other types of transformations, but that might have certain drawbacks or might have certain additions too. It depends upon what sort of transformation you're using, right? So in that case also maybe Z2 has the highest probability, but maybe not as high as what it would have been if you use, say, such a transformation, right? So we need to see that.
And I think the one of the reason this like softmax will work is that we are penalizing the negativity, right? So on the negative side, we are not trying to see if they are all negative. We don't want everything to be check on maximum value. So it makes a difference.
Yeah. We want the model to predict certain high activations for certain inputs, right? That's when we say the model is trained to some level to predict what is happening, right? So we don't want it to do that. But that does not even matter if I say Z is a sigmoid here, right? Then Z will not have negative values also, right? So you will only consider this part of the Z space for in that case, right? If I don't think, say, this is not a tan H, this is a sigmoid, right? So Z won't have a negative value. So this part of the space is not even considered. So only this will be considered. But then that makes a lot of sense because now if you see small differences between Z, that will be amplified, right? And as you see that as you come close to the y-axis here, right, as Z comes closer and closer or becomes smaller and smaller, the function is slightly more linear, right? But then as you go higher and higher, it becomes more non-linear, right? E power Z, it blows up. So you can see that if the values are very small, then the probability distributions will be mostly flat. But then if some value increases, then the amplification happens. And that's what, the softmax gives you at the end of the day. Okay? All right, guys.
So, sir, as name suggests, softmax means taking the softly the decision.
Yeah, basically it's in the name, right? It's a soft max.
Yeah.
Right? It's not a hard max, right? It's not taking basically the maximum value that is there. Just
clearly means जो ज़्यादा probability दिखा वही ले लिया.
Yeah, exactly. So that's the idea of a soft max. So you're being, so in some sense that if you had picked a hard max, right? Things where it is 0.1, 0.05 and 0.05 in such a case, right? Hard max would be the prediction that this is fine. But under when you put it under this probability distribution, then very likely everything is probable in that scenario, right? I mean, one of them will still have a higher probability, but what I'm saying is you have to sample. You just typically people assume that you take the highest value of the probability, that is what it is. But typically what you have to do is you have to sample the probability. You have to toss a coin, find out where it lands. And in this case, it will highly likely land always on Z1, right? So you should think of it like a three-sided coin here. Yeah. If it's a three-sided coin, then you toss it. Most of the times it will land on Z1. That's what this probability distribution tells you, right? In this case, it's equally likely that it will land on Z1, Z2, or Z3, right? When you toss the coin. So that's the idea. Right? So that's the difference between a hard max and a soft max. Yeah, very nice. Yeah, thanks for pointing that out. Okay, guys. So I hope this is fine. So with that, what I'll do is we'll cover the last part of CNNs, because I thought for the sake of completion, I should also tell you a little bit about the backpropagations in CNNs, right? Like we looked at backpropagation in a normal feed-forward neural network. It's important to understand the concept in CNNs, because most of the packages that you will use, they'll always have inbuilt functions or inbuilt scripts to do this, right? But it's important to get an idea where this intuition comes from. How do you actually do backpropagation to understand, right? Like you just don't want to run the code and get your answers, right? You want to understand what it actually means. So let's quickly look at that today. So you all know the forward propagation in a CNN. So let's take the most simplest case and work it out there, so that you understand how this will extrapolate to even complicated deep layers, right? So let's say this is your input image, or this is some previous layer output, okay, that is going into your kernel. Let's take the weights to be the kernels here, right? Because that's what it is at the end of the day. Your weights are your kernel, right? And the image is convolved with the kernel. And then you either pass it through a nonlinear activation function, something like a ReLU or something, and then you get your layer activation, right? Now I'll tell you how I got Z1, Z2, Z3, Z4, but this is your forward propagation, typically, right? So that means that first you place the weights here. Now let me consider I'm doing a stride of 2 here, okay? So I'm not moving every other pixel, I'm moving every other pixel, okay? And then I shift it, I get Z2, then I get Z3, and then I get Z4, all right? So this is forward propagation. And let's say this is my final layer activation, and then I flatten this layer out. I do some, let's say I just have final 1y output prediction, y hat, and then I compute the loss function, right? So this is the forward propagation in CNNs. Everyone's okay with this? Everyone's clear with this idea, right? Like this is what happens. Okay. Now let's talk about backpropagation. How does that work? Now, can anybody tell me what are we trying to figure out with the backpropagation here?
Errors.
No, what is the aim of backpropagation basically?
Means I want to give out
Improve the model.
differences in
Yeah.
output.
Yeah, we want to find the weights. We want to optimize the weights,
minimize
right?
the loss.
Yeah. We want to find those weights that minimize the loss, right? Exactly. So if I have to do, so how do you optimize the weights? We can use gradient descent, right? Like how we have looked at before. Now, how will gradient descent be applied here? Can anyone tell me? Or try and guess. So these are my weights, right? So let's call them some W i's.
So dz by dw.
Yeah. So that would be, so on a common, so your new WIs will be old WIs. So you want to do gradient descent. So you want to go negative
Minus
with some learning rate eta, right? And what is the what is the gradient here? What are you trying to minimize?
delta L by delta W.
Dou L by
Delta W.
right? So you are trying to minimize your losses as a function of change in W, correct? This is what you are trying to do. Very simple. Yes, everyone with me? So that's basically that, right? Now, point is, what do we have to find? We have to find dou L by dou Wi's, correct? This is what we want. Now, how do we find this? That's the main crux of the problem. So think about this, right? Let's say I change W1, okay? If I change W1, how will the next layer activation change? Will everything change, or will only some things change in CNNs?
Everything changes.
Everything changes. Why? Because
Z1 is dependent on
W1. Z2 is
W1.
also dependent on W1 because you move the kernel over the image, right? And that's how you get Z1, Z2, Z3, Z4. So that means a change in W1 will create a change in Z1, Z2, Z3, Z4, which will in turn create a change in the output, which will change loss. Correct? So that means if I take dou L by dou W1, right? How can I write that, right? That basically is nothing but dou Z1, correct? That is the change in Z1 with respect to change in W1, correct? I'm using the product rule. And then anybody?
Dou W1 upon Y.
Dou Y hat upon
dou Z1,
dou Z1, correct? The change in Y hat because of Z1.
dou loss function,
Yes, dou loss by
dou Y hat.
dou Y hat. Okay. So this is very simple. Now this is for just the change in Z1, right? Now you have to add the next part, which is what? Dou Z2 by dou W1, right? The change in Z2 because of W1 times dou Y hat by Z2 because the change in Y hat because of Z2, and then the change in the loss because of Y hat, right? Now plus dot dot, right? Like we have other stuff. Now what is this? Can you use chain rule and then simplify this? Anybody?
Dou L by
Dou L by dou Z1.
Dou L by dou Z1. That's it. So you can just write this as dou L by dou Z1. Right? This. I don't want to cancel it out like that, but I'm just giving you an idea. Right? Don't do that. This is not correct. But yeah, I'm just gonna control Z that. No, I can't. Okay, fine. But you get what my point is. Yeah, so you can write that. That's the chain rule of partial derivatives, right? You can write it like that. Okay. So let me erase this because I have that here. So this is basically the kernel update then, right? You want to find out dou L1 by dou W, dou L by dou loss by dou W2, and so on and so forth. So that means that you have this, correct, as we derived, and then this becomes this. And so your dou L by dou W1 is nothing but dou Z1 by dou W1 into dou L by dou Z1, and so on and so forth. Okay. People are with me till now? Everyone good? Any questions? Cool. Now let's take this.
Sir, sorry to interrupt.
Sure.
Sir, could you please accept some people who are still waiting in the lobby?
So that's what I'm trying to say. You should use your IIT email ID to do it, right? Then you'll be in the class, or you send me the email IDs, right? I mean, I asked Ashutosh the other day, he sent me stuff, but let's see. No, there is no one waiting in the lobby. So there's no one. Yeah. Join with your IITJ email ID, guys, so that you don't have to wait in the lobby, right? Be easier. Okay. People are with me till here? Yes. Now.
Yes.
Now let's look at this part now. Let's look at what happens to this. Okay, this equation. Okay, because it's nice after this. Okay, let's put it up. So update for W1 is like this, right? Dou L by dou W1 is this. Now, you know what Z1 is, right? What is Z1? Z1 is that convolved form of the input weights with the convolution of the kernel with the input for a specific space of the input. Yeah, for the specific space of the input. Correct. First convolution, exactly. So what we have now then is something like this. So if I can expand it out, it'll be Z1 will be W1A1 plus W2A2, W3A3, W4A6, W5A7, and so on, right? So if I go back one step, so it's nothing but A1 into W1 plus A2 into W2, A3 into W3, A6 into W4, A7 into W5, A8 into W6, and A11 W7, A12 W8, A13 W9, right? So you can write Z1 like this, right? Similarly, you can write for Z2, Z3, and Z4, right? You can write that. Now, one thing I'm sort of missing here is this should be G of, right? Where G is your ReLU function or nonlinear activation function. But for the sake of simplicity, let's just not have it, okay? Because anyways, when I partially differentiate this, this will come out as G dash of that Z1, right? Which is more or less constant if I'm thinking of taking a ReLU function, right? Because I mean, that will appropriately multiply, but for the sake of simplicity, let's not consider the G dash part, okay? So now tell me, what is dou Z1 by dou W1? That means you're taking the partial derivative of Z1 with respect to W1. So that means that everything that is apart from W1 is a constant.
A1.
A1. Right? So then
Yes.
dou Z2 by dou W2 will be?
A4.
Multiplier of W1 will left, otherwise other will become 0.
Yeah, no, with respect to W1. So you're still doing it with respect to W1.
A3, no?
A3.
A3. Very good.
A1 plus A2 plus 8, A3 plus 8, 11.
A11, very good. Yeah, dou Z3 by dou W1 is A11, and then dou Z4 by dou W1 is
A13.
A13. Okay. So basically, what we are able to simplify this to is your activations A1, your input A1 with your loss with respect to Z1, right? A3, and then change in loss with respect to Z2, A11, and A13, and so on. All right. So this is pretty simple. So like that, now we can come up with, say, 9 different update equations, right? Which is dou L by dou W1 and then W2, W3 till W9, because it's a 3x3 kernel, right? So we have 9 weights. So let's look at that, right? So this is your back propagation, right? That is, you have the loss at this level, right? Dou L by dou Z1, dou L by dou Z2, and so on, so forth. And now you are pushing this loss through this weight function, right? And you'll have these 9 equations, right? For each W1, W2, W3, and so on, right? Now, everyone is okay with this. Everyone gets how we got this. It's the exact same things which we saw for dou L by dou W1. And now you do that for with respect to every weight, because we want to, at the end of the day, find out the kernel push this weight based upon our loss. Okay. Now, can anyone see a pattern here? Anybody can tell me? Can they spot something?
You can vectorize it in the form of matrix.
Very nice, very nice. So if you take, let's say this, right? What's that? A1, A2, A3. So if you take all the updates that belong to dou L by dou Z1, that is when you push this guy through, what happens? You get this part of your input space. So A1, A2, A3, A6, A7, A8, A11, A12, A13, right? And so on and so forth, right? Like then you get this part for the next one. And then this one for the third one. And so on. This one for the fourth. Right? So for each loss with respect to Z1, you get the individual, you see that this can be written in a matrix form, where if I take this to be the, the situation right now, the kernel update would be A1, A2, A3, A6, A7, A8, this part times dou L by dou Z1 plus this part times dou L by dou Z2 plus this part by multiplied by dou L by dou Z3, and then finally this part. Okay. Everyone with me here? Right? So it's nothing but these equations, right? These 9 updates. I'm basically writing it this way, right? So what does this mean, right? That means that the change in the update at this weight kernel is nothing but the convolution of your your individual losses at Z1 with summed over the input space that the kernel occupies, right? So basically that's this equation, right? That means that this part of the input space that the kernel looks at, right? If you just slide the kernel over it, these are the input space that it will look at, and you multiply those input spaces with the individual losses that you see for those spaces, right? In this case, that is dou L by dou Z1, right? And dou L by dou Z2, and then so on and so forth. Okay, that is the kernel update. And now how do you update the kernel? Basically, then you just take the weights and then you say, I'm adding some learning rate times this kernel update. Okay? And that way you update the weights at every level using the errors that have been backpropagated from the previous, from the layer that is ahead of it. Everyone good with this? Any questions?
The DL by in
No,
the
sir.
last iteration,
This
DL
one?
by so DL by DZ1.
Yeah.
This will be a single value, or it will be? I'm just getting confused.
So it will be a single value because it is for a given Z1, right? It will be a single value.
Okay.
Yeah.
So in a way, it will be convoluted to the. But sir, you have taken a stride of 2, right?
Yeah, in this case.
But if it comes, I mean, can it be generalized further?
It can be. It can be I mean, the stride of 2 makes a lot of sense here to explain. You can do it for a stride of 1, 2, right? Instead of then this being a square kernel, it will be a rectangular kernel. You'll have Z1, Z2, Z3, right? Because you have this, you have this. Oh, this way also, actually it will be a 3x3 output as well, right? Because you'll be here and then you'll slide here, then you'll slide here, then here.
That.
So it'll be 3x3. Then you'll have Z1, Z2, Z3, Z4 till Z9, right? Z6, Z7, Z8, and Z9, right? And now you'll have dou Z1 by dou L by dou Z1 and so on and so forth, right? So it could still be generalized to any sort of stride. I just, for the sake of simplicity, we took a stride of 2.
So it is not exactly convolution, right? Because it is a 2x2 matrix, and doing that on a
right. So what I'm saying is, so when you convolve the input, right, with the weight kernel, this is the output. If you go back, it is as if you are pushing it through this kernel, but maintaining that space of convolution, right? Like you take your Z1 and you multiply it only with that input space from which this information was obtained, right? So dou L by dou Z1 is multiplied with only this part of the space.
Right, so that I understood. It's just understanding of the convolution, because that would have taken only A1, A2, A6, and A7, right?
No, because W1, W2, W3 will be placed here, right? It will take this entire.
If we take the 2x2 matrix.
If I come back to this, right, I'll show you the forward propagation. If you remember, this is how the convolution works, right? So. Yeah, so you place W1 on this. That's how you get Z1, if you remember. And then Z2 this way, Z3 this way, Z4. So imagine now this becomes dou Z1 by dou L by dou Z1, right? So that is as if you are pushing the error through these weights. and then using this part of the input space. Yeah. And then for Z2, you use this part of the input space to update. And for Z3, this, and then for Z4, this. Okay. Imagine the feed forward case, right? In feed forward case, if you remember, you only use eta, delta, and x, right? You use the input that is coming to that layer to update. But here you follow that same convolutional, arrangement or the logic when you are trying to update. Okay. So that's what ends up being this. Right. So in sense, A1 dou Z dou L by dou Z1, A3 dou L by dou Z2, A11 dou L by dou Z3, A13 dou L by dou Z4 gives you the update for one of the weights. Dou L by dou W, right? And then so on and so forth. Right? So this is how it works. So this is the mechanics of it for you guys to understand. I would suggest I'll share these slides. You can go over this once more in your free time, sort of find out how this works. But hopefully the idea becomes clear, right? It's multiplied with the part of the input space over which the Z1 was actually changing in this case, right? Because Z1 is being influenced by only this part of the input space. So when you are actually taking the change in W1, you should take the change with respect to Z1 for that particular input space.
Means that loss will be impacted all the from where W1, I mean Z1 was calculated, right?
Correct. Yeah. Loss is going to be impacted with change in everything, right? Like if you change W2, loss will get affected.
Yes.
W3, loss will get affected. But when you back propagate it, you should do it in such a way that then the change in W1 is being reflected for those things that can actually affect W1, right? And that's what we sort of unraveled from here.
Means Z1 will going to multiply with all the submetric of Z1 where it is calculated.
Exactly, right. Exactly. Because if you imagine a change in W1 is going to affect all Z1, Z2, Z3, and Z4 because W1 is common, right? That is the kernel that's common for this input space. But when you update W1, for example, when you do this update, you have to see that this matrix form can be obtained as a sort of a compact representation of how the back propagation happens. But if you see the individual terms, the change in W1, that is dou L by dou W1, is still a function of all the Z's, right? A1 into dou L by dou Z1, A3 into dou L by dou Z2, A11 into dou L by dou Z3, and so on. Right? So at the end of the day, the change in the loss because of W1, when it's getting back propagated, you get information from all the Z's because it is affecting all Z's.
And so like in W old, we are subtracting this multiplication, right?
Yes, we are doing
learning
this.
rate.
Yes.
So that our assumption is like that we want to remove this loss from this.
We want to update the W in such a way that next time the loss becomes smaller. Exactly.
That's why subtraction is referred here.
That's what the gradient descent comes in, right?
Yes.
Like the loss function has some minima, and then you are going towards the minima of that function by going towards the negative of the gradient.
Gradient is 0.
Yeah. Okay, everybody with me? Yes. Are there any more questions? Happy to answer. All right. So with that, let's summarize what we have looked at in CNN till now, right? We have looked at convolution, the idea of convolution, the idea of extracting relevant features from data/images, right? And the idea that when you do backpropagation, you are trying to minimize loss. And it happens so that when you do this, the convolutional kernels that you get are the kernels that can extract those features from the data that will minimize the loss. And this could be anything. Like detecting edges, detecting certain specific features, certain nonlinear combination of features, and so on. And then we saw the idea of pooling, where it is to downsample the image to reduce the feature dimensionality. That is it possible from a given layer of features to pool the features in such a way that can maximize, say, contrast, smoothen the image, pick darker regions of the image, if you do a min pooling, for example, are there ways to do this to reduce the feature dimensionality? Then the idea of dense layers and softmax, and this is something that can change depending upon what sort of application you want. At least if you're performing classification or prediction, this can help you. This dense layers and softmax can help you in that. But that is what we saw. And finally, the idea of backpropagation. That is, you are pushing the gradients through the convolutional layers, and you can imagine that there is a problem of vanishing or exploding gradients even in these problems, where people have now come up with many different types of networks, right, which can tackle some of these issues. But the idea is you're pushing the errors through the network, through these convolutional layers, right, and updating the weights. So it is natural that the deeper the layers are, the more either the gradients will vanish as you go deeper and deeper compared to the shallower layers that are close to the output error. Or if the it could also go the other way, that the errors can explode, right? It becomes bigger and bigger and bigger, so that the initial layers become very unstable. So we saw some ideas of backpropagation as well. And final thing I would like to say is, I would like you to do a little bit more reading. One paper I would suggest is by Lee et al. In 2022, which is a survey of convolutional neural networks. It's a very nice paper. It talks about the history and possible applications that have been till now, because there have been many such variations of the convolutional neural nets, like for example, Google's Inception architecture, right? And then later ResNet and all that, where ResNet has a very interesting way of tackling the vanishing gradient problem, right? As we talked about, as we go more layers and layers, and then you have a fully connected layer and then output, the errors that you get at this point, or the loss, as you backpropagate them, the change becomes smaller and smaller and smaller as you go, right? It's very big here. You feel it. It's like you feel the error a lot here, but you don't feel it here. So how do you tackle those? And the ResNet has answered that. And then there are many sort of combinations. VGGNet is one where it is a combination of several deep layers of convolution followed by just 3 layers, 3 dense layers at the output. And VGG nets have also been used as a way to explain some brain data as well. I showed you that in the last week, right, when we were discussing about this. And then there are many such, there are mobile nets which are, small versions of these networks, which can actually be done over, they can be embedded in, certain architectures like CPUs, which have even low computing power, I believe. So those are that. And then there are many such things that have come up in the recent times as well. I would urge you to go back and read some of these to get some ideas of CNN applications, right? But with that, I think we are done with convolutional neural networks. Tomorrow we'll start recurrent neural networks, right? And see some ideas behind that. But if there are any more questions, I'm happy to answer them. We have like a couple of minutes, I think.
Sir, I have a question. Like I have actually seen questions like from CNN that how like that calculation of parameters into layer by layer. Like after first convolution, the number of parameters are this and this, and even in the last semesters, we actually had this question that I actually didn't, I wasn't able to answer.
Okay.
So like these type of questions I have seen a lot. So can you just can you explain how to approach these kind of
and so give me the question. What is the question?
So basically it goes something like this, like let's say we have a CNN architecture, and there is an image, let's say 28 by 28 pixels, and so after that we have a certain, let's say a kernel of 5 by 5, and and after that we have again another a CNN layer, a convolution layer, and so on. So basically after each iteration, like after each layer, how the parameters.
I see. You mean to say that what is the output of a convolution given a set of size of image and the kernel, and
Exactly.
given
So
certain
what is the final
parameters. How?
sizes? Exactly.
Okay, final sizes. Hey, so okay, you know what? We will more probably do one class of that, like, or at least a couple of minutes of that, because it requires some formula, and I'll let
Yes,
you know
exactly.
actually it's a very simple calculation. In fact, you can start off by looking at the image size, the kernel size, the stripe that you are using, the padding that you are doing, and there is a very nice, neat formula that we can use. In fact, we can have a look at it maybe tomorrow at the end, right? Just give me a reminder.
Sure.
Right?
Sure.
We'll talk about RNNs. We'll start that so that the discussion can
And
go. We'll do
I'll
that.
just find the question if I have it.
Of course, yeah,
in the last
please.
semester.
Sure. If you find it, send it to me. We can
Sure.
try and solve that. In fact, I should have put it here. I'll add that part up, right? Like if you're using different types of parameters for the convolutional layer, how does that change the output image size, right? And if you have 3 layers, 4 layers, and so on and so forth. So we can do that. Sure. Sounds good.
So, sir, what type of questions we will expect in
in this? We will expect mostly things which are conceptual, right? You'll be given things that will make you think rather than sort of remember, or you don't have to remember too much, is how my policy is, right? You don't have to list the convolutional neural networks or the types of them. I don't like to do that, but it will be more conceptual, saying that what is the idea of backpropagation, how do you explain that, so things like that you can expect, right? And we'll talk about anyways, minor 2 is also going to be there in a month, but that will be different. But these are the types of questions, more conceptual is what I would say, right? Is what you need to concentrate on, right? The idea behind the interpretation of pooling, like what is the idea of max pooling, and what that gives you, for instance, right? If you can explain it with an example and concretize it, then that's good enough for me. Okay. All right. Okay, guys. So that's it for today. We are at 12. I'll see you then tomorrow at 9:45. Have a good rest of the day. We'll meet tomorrow. I'll stop.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.